I'm Bert Holmes. I'm a chemist, obviously, and this is Chemistry 132. I try to start class on time, so we'll be here by 10, if at all possible. So what you've been given is a syllabus. So get the one-page syllabus. This is a brief one. You'll notice on the top it says brief. There's a longer form syllabus on Moodle. Do all of you understand Moodle and how to go to Moodle? Anyone not understand Moodle? Okay, so go to Moodle and you'll find the full syllabus. You want to read that. This has critical information. I'm going to go through a couple of quick things today. My office hours are there. My office location is there. Number 4, under important information, is the Friday afternoon session. Normally used to make certain everyone understands all concepts taught that week. So we're going to meet most Friday afternoons. But it won't be in this room. It'll probably be upstairs in room 123. I'll let you know for sure on Wednesday. You should also be enrolled. Number 5 says you should also be enrolled in the Chem 111 lab. Is anyone not enrolled in the Chem 111 lab? Okay, because if they're all full. Okay, so keep checking. I mean, maybe you don't really need it, but keep checking. And if there's one you want to go to it. And if somebody's not there at the first meeting, the faculty member can drop them and put you in. So the textbook, everyone have a textbook? Should look like this. You're going to need one of these. The grade points that are available in this course are listed. You've got 100 points for homework and worksheets. Each exam is 100 points. There are 3 of them, 300 points. Quizzes are 100 points. The final is 200 points, in total 700. The same grading distribution is used for all 7 of the Chem 132 sections. The grade distribution, the grading scale, is the same for all Chem 132 sessions. The exam dates are all the same for all Chem 132 sessions. Everyone takes exam 1 on September 19th, various places across campus. They take the exact same test. So we're very consistent among the different Chem 132 sections. There's information on the back of that first page about quizzes, about the homework. The homework is done online in a system called SmartWork. And in the book that you get from the bookstore, there's a scratch-off card that has your student access ID number. And you're going to need that. So if you bought the book separately, like as a used book or online, you're going to have to buy this from Norton. Everyone needs a SmartWorks ID, and I'll tell you how to access that in a second. All right, so look under student self-registration, middle of the back page, right? You need a valid email address. That must be your UNCA email. It's got to say unca.edu or Norton won't let you sign up. You have to have the enrollment key for my course, which is listed there. It's chem@6903. You see that? So you're going to need that. And you're going to have this registration code that is in the front of the book. So what I want you to do is go to SmartWorks as soon as you can. Get yourself set up in this course. I'll check it before class on Wednesday and see who's done that. Also in SmartWorks there's a getting familiar with SmartWorks, number 2 on the assignment. You should do that. It just tells you how to enter the answers in the correct format. So do that. You'll have a homework assignment this first week, but not just yet. Go get signed up. Everyone gets signed in. Do your practice on how to use it, and then we'll give you your first homework assignment. Now, I'm going to give you several pieces of important advice. So the first part, this first lecture, is going to be about how you can succeed in general chemistry. And then we're going to do a problem. That is, I think, sort of the important thing to learn from the first chapter. So here's my advice. I'm going to read this because I think it's that important. You're going to find that you're going to need to spend probably 2 hours every day studying chemistry. Some need more than that. Some can get by with less depending on how much high school chemistry you had. Who did not have high school chemistry in here? Anybody? Everybody did. Okay. Who didn't have a good high school chemistry class? Yeah, well, me too, by the way. I went to college, I wanted to be a basketball player, a basketball coach, and a math teacher in high school. I hated chemistry in high school. You know why? Because he didn't know any chemistry. And it turns out that only about a third of the teachers of chemistry in North Carolina were actually chemistry majors. Most of them majored in something else, and they don't know chemistry very well. So you're going to find that you're going to need to spend 2, maybe 3, maybe 4 hours every day studying chemistry Monday through Friday. Saturday, you should review stuff from the past week. Review stuff you learned on Monday, review stuff you learned on Wednesday, review stuff you learned on Friday. And then Sunday, you want to review stuff from the beginning of the semester. Remember that, what I just told you, okay? Okay, you can go with a Moodle and get the full syllabus at 7 pages. So why would you study chemistry? And what's the approach that we're going to use? We're going to use what's known as a molecular perspective. We think about molecules. That matter is made up of atoms. And atoms combine to make molecules. And those atoms and molecules determine what chemistry is going to happen. And so we're going to take this approach of, let's understand the atom, and that'll help us understand how the atoms and molecules combine and do chemistry. So I've been teaching this class for 40 years, probably longer than some of your parents are years old. I've done this a lot. What I've found is that students struggle with dimensional analysis, which is section 1.9. An important point is, what I've also learned is that students don't know the learning of chemistry is different than learning other subjects. Most students don't know that, but it is. And I'm going to give you some examples that I hope to convince you of that. You've got to study chemistry differently than you might study history or art. So I believe in a fairly interactive classroom. If you have questions, raise your hand. I may call on you. You guys can ask me questions. All right? So your first assignment is to learn the names and symbols of the first 36 elements by the next class. That's H, which is 1, through krypton, which is 36. Learn the symbol and the name spelled correctly. Now, if you don't learn it till Friday, that's okay, because the quiz is on Friday. But try to get it learned by the next class period.
Question.
Yeah.
Is this Chem 132?
Last time I checked.
Okay. A lot of us were confused because there were so many people already here and calculus people were walking out.
So pick up one of the, there's 4 pages on the front. Pick those up.
Okay.
Everybody get one of those.
Sorry about that.
Or you can come over here and pick some up from here. I wondered where everybody else was because there weren't enough kids in class. You guys can't read where the course is supposed to be? What's going on here? Yeah, Brenda. Yeah. I was worried there weren't enough kids here. 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 You have, oh, here. What do you need? One more? Pick which one you need. Which one you need? This one?
That one, yeah. Thanks.
I need like one of everything. Thank you.
Did you get one of these?
Yeah, I did.
You need everything? All right, all you latecomers. This, by the way, has never happened. I never had a class I started and 10 minutes in, it's interrupted by about a third of the class. Yeah. So there's a chem information sheet for you newcomers. Fill that thing out and leave it with me today before you leave the class. So work on that while I'm talking to you. Or when I'm not talking, maybe work on it. All right? The other thing you have is a schedule and a CSI, which is Chemistry Supplemental Instruction. Those you're going to fill out and turn in Wednesday when you come to class. Don't work on those now, you can work on them Wednesday. The syllabus, we just finished covering that. So go over that and look at it. All right, so we're going to jump back in where we were. So I'll start back at number 1. Learn the names and symbols of the first 36 elements by the next class period. That's 1 hydrogen, H, and how you spell it, down to krypton, Kr, and how you spell it. Learn those by Wednesday. All right, so really you have to learn it by Friday because that's when the quiz is. But learn it at least by Friday. And later we'll ask you to go from 37 to 92, which is uranium. Okay. Read and study sections 1.1 to 1.8. These are things that are covered in the freshman chem lab, Chem 111. And read section 110. So that covers things like significant figures, accuracy, precision, rounding numbers. That's all covered in Chem 111. Memorize the commonly used prefixes, and I'll get to those in a second. It's table 1.1, and it's kilo, centi, milli, nano, and pico. And I'll get to those in a second, so don't worry about them right just yet, okay? Go to SmartWorks and sign up for this class using the access code that is on the middle of the back page of the syllabus and your particular access code that's in the book you're going to get from the library, which is here, scratch off code. So sign up for SmartWork by next class period if at all possible. Okay. So why study chemistry? Well, it's called the central science, and it's important in improving health care, conserving natural resources, protect the environment, increase food production, new developments and new materials. Almost everything you're looking at in this room was a result of chemistry, including you. It's by its very nature, as I said, the central science. If you're in astronomy or atmospheric sciences or biology, geology, environmental science, they all require chemistry because chemistry is the central science. And the language of chemistry is universal. So how do you study chemistry? So these are some important things I want you to get. And I often find that it's useful to write stuff down because if you write down notes, it means it went through your brain one time. If you just look at it, it didn't necessarily go through your brain. It kind of got partway there and then it quit. So I really believe in taking notes. These notes are going to be available on Moodle. They'll be posted later today. You can go print them out. So they're going to be there. So who was Michelangelo? Sculpture, artist, anything he did that you might know about? The David. David's a beautiful sculpture. I've seen it. Have you seen it? It's much smaller than you anticipate. What else has he done?
Ninja Turtles.
What else has he done? Painted the Sistine Chapel. So if this is a painting class to paint the ceiling, or to take a piece of marble and make a sculpture, do you think he'd teach the class?
Probably not. I don't imagine he'd like teaching.
Yeah, but do you think he could teach the class?
Probably, yeah.
Yeah, he probably could teach the class, couldn't he? Yeah, he could. And Michelangelo was born in 1475. You got a block of marble here, he'd teach you how to sculpt that into something like the David, which is phenomenal. Yeah, he'd be the teacher. Who's the father of chemistry? Anybody know?
That one guy.
Who's the father of chemistry?
I feel like that's a trick question.
Anton Lavoisier. So would he be the instructor in this class if I weren't here and he was here? You're shaking your head no. Why not?
Because things have changed, or not changed, but we've learned more.
We've learned a lot about chemistry. He thinks the formula for water is HO. Is he right? No. You all know he's wrong. He's never heard about polymers, nuclear chemistry, ceramics, alloys. He knows a couple dozen elements. By Friday, you're going to know 36, far more than he knew. He's lost. Every one of you knows more chemistry than he does. So he would not be the teacher. But then again, neither would you. So what's different about those two people and those two disciplines of art and chemistry?
Art doesn't evolve much. Chemistry is constantly changing.
Chemistry is constantly changing. It's constantly building on itself. I'm going to give you a couple of examples of that in a minute. Okay. So you must study chemistry differently. You must study it every day. And what did I tell you? How many hours every day? 2 to 3 or 4. The best predictor of your final exam grade or your final grade in this course is the grade on the first exam. That's your best predictor. You must correct misconception as soon as possible so you don't fall behind. You can't misunderstand something and think you've got it and you've got it wrong. So we want to fix those misconceptions. And it turns out there's a lot of misconceptions that students can get about chemistry. So how do you study it? Another example. Well, I say that chemistry knowledge is hierarchical or pyramidal or sequential or whatever term you want best to describe it. I don't care. But those are the terms I would use. It all builds on itself. So here's the question. How many molecules of carbon dioxide can be produced by heating of 15.5 grams of lanthanum carbonate? In about 5 weeks, you'll be able to answer that question. I'm going to walk you through the solution now. You don't have to write this down. Just look. Because there's a bigger picture you want to get from this example. Okay? It turns out to solve this problem takes about 10 concepts. And we're going to cover those 10 concepts in the next 3 or 4 weeks. If you didn't learn one of those concepts because you fell asleep or you missed class, can you do the problem? No. You're lost. You're screwed. You can't do it. So it's important to learn every concept that we teach you because the next period we're going to teach concepts that build upon that one. It all builds on itself. It's hierarchical. It's pyramidal. Whatever term you want to use. So you've got to study chemistry differently. So if you're in a history class and it's covering history from 1800 to the First World War, and you didn't learn that stuff because you don't like the Civil War, but the next test covers World War I to World War II, and so you study hard and learn that stuff, you may flunk the first test and get an A on the second test. That is not going to happen in chemistry. Because the second test is going to assume you know material from the first test. It's going to build upon stuff you learned in the first test. All right. So, how many molecules of carbon dioxide gas can be produced from heating of 15.5 grams of lanthanum carbonate? First thing you have to know is what lanthanum is. You've got to know that it's right there on the periodic table, 57. It comes right there. You must be able to predict that its charge is 3+, which will teach you how to predict, and you could get it from the periodic table. You must know that carbonate is CO3 2-. So you can write the proper formula for lanthanum carbonate. You have to know that a metal carbonate, when heated, decomposes to metal oxide and carbon dioxide gas. We're going to teach you that. And you've got to balance this equation right, that there's 1 mole, 3 moles, and 3 moles. And you have to understand the mole ratio, that 1 mole of this produces 3 moles of that. So when you work this problem, 15.5 grams lanthanum carbonate. I use the molar mass of lanthanum carbonate from the proper formula. I use the mole ratio from the balanced equation. I use Avogadro's number for the number of moles and molecules. Avogadro's number of molecules in a mole. And I cancel my units, so grams cancel grams, moles cancel moles, moles cancel moles, and I get molecules. I get the answer, the right answer. Okay, so to work this, I must know the formula for lanthanum carbonate, number 1. Number 2, predict the charge on lanthanum ion is 3+. Formula and charge of the carbonate ion. The formula for lanthanum carbonate and carbon dioxide. A chemical reaction. How to balance it. The molar mass of lanthanum carbonate. The mole concept for a balanced chemical equation. How to do stoichiometric calculations. Avogadro's number. How to do dimensional analysis. If I know all those concepts, I can get it right. If I don't know one of them, I'm screwed. Well, I'm not. Y'all are. Yeah. Right? Are you convinced yet? Now, you probably knew this from high school, right? This was taught to you in high school. Yes? No? No?
Divine taught.
Okay. This is probably a new idea that you've got to study chemistry differently than you study other subjects because it's different. What terms would I use to describe it? Sequential, pyramidal, hierarchical. Right. Its knowledge is different. So you've got to study differently. Okay. So what do you want to bring to class? Lecture notes from Moodle. You can download them, print them out. They're It's not as early morning as it could be, but it's early enough for me that I need a little coffee. In case you're wondering, you're all a little boring, so this coffee helps me keep going. And I understand I'm boring, so coffee will keep you going too. A keen pair of ears, inquisitive mind, bring a calculator, any calculator. I don't care what kind of calculator, but not your smartphone calculator. Those are not allowed because you can text. So you can't use those on a test or a quiz. Bring some opinions. This class is fairly interactive, and we'd really like to have a good attitude about learning some chemistry. All right, some strategies. So what we know is that we're going to work in groups with worksheets. Because what we found as we studied how students learn science is you learn it with peers. And you learn it best when you can interact with peers. So this chem information sheet that I asked you to fill out, everybody got those filled out yet? You done? Pass them towards the middle. If you haven't got them filled out yet, then fill them out as soon as you can, and turn them in at the end of class. So I'm going to use these to assign you to groups. And how am I going to assign you? I'm going to put all the smart ones together, right? No. How come I keep getting more from you guys? We're going to assign you based on who's had more experience, less experience. We want the groups to be fairly balanced. But we're going to work in groups. And whether we're going to do it is there going to be a group of 4 here, a group of 4 there, and a group of 4 there, a group of 4, 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 and a group of 4. 10 groups. Yep, 40 kids, 10 groups, 4. Okay? And we'll assign those groups on Wednesday. And there'll be a worksheet for you to do on Wednesday. There'll be a quiz each Friday. It will test whether you learned the important concepts taught that week. It'll be given Friday morning, typically. If I can get it graded by Friday afternoon, and since there's 40 of them I don't know, we'll see. We'll meet Friday afternoon, and we'll correct any misconceptions. I'll say, you know, you guys really didn't understand this mole idea. Let's learn that again. Let's see what the misconceptions are and fix those. So when you go to next week, you'll be up to speed. We're going to do a lot of group work. I've already mentioned that. I'm going to assign the groups. I encourage you to study together in class and outside of class. So you'll find, for example, if there's 8 of you that live in Mills Hall, there'll be 2 groups from Mills Hall. As an example, for 4 of you that are commuting, there'll be a commuter group. All right. So we want to learn these base units. You already know them. Mass is kilogram, length is meter, temperature is Kelvin, time is seconds. Current we don't really use, but moles is a quantity of substance. So you can look at that on page 19. We're going to learn these prefixes. Kilo is 1,000. Centi, 10 to the minus 2. Milli, 10 to the minus 3. Micro, 10 to the minus 6. Nano, 10 to the minus 9. Learn those 5. The kilo, the centi, the milli, the micro, and the nano. Learn those 5. Memorize them. You probably know most of them, but learn them. So we want to learn things about units of mass and length. We want to learn these conversion factors between the British unit and the metric unit. So what I tell students to learn is 2.54 centimeters is 1 inch. 454 grams is a pound. Learn those. 1 quart is 0.946 liters. So in every case, what I've given you is in British unit related to some metric unit, and British unit and a metric unit. You should also know that 1 cubic centimeter is 1 milliliter, or there's 1,000 cubic centimeters in a liter. You should learn those as well. So calculations, this is section 1.9. This is probably, I think, the hardest part for students to learn. So we're going to spend some time on this in this class period. So this process is called dimensional analysis, or factor label method, or unit conversion method, or one factor method. So how many use this in high school? Something like this. Does that ring a bell? So how many, this doesn't ring a bell? Oh, a lot of you. Okay. Interesting. Usually it's the other way around. Okay, so we're going to learn this unit conversion method. I call it dimensional analysis because you're analyzing the dimensions. The dimensions are the same as units. So it's a problem-solving aid. It's a systematic way to approach problems. We need to learn how to do that. You oftentimes will see on a test or a quiz, it will say, using dimensional analysis, calculate something. So it works for many calculations, not all, but many. A key component of this are conversion factors. Things are related to each other. Okay, so let me give you an example. Lawrence, right? The reason I know that is I was born in Lawrence, Kansas. Lawrence, how tall are you? Just guess. 5'6". Okay, how many inches is 5'6"? 66 inches, right? So I got one Lawrence. Is 66 inches. Right? That's what one Lawrence equals, 66 inches. What I want to know is how far is it, do you think, from this wall to that wall in meters?
6. 5 maybe.
Meters a yard. 5 yards is about right here. Huh? 12. Okay, we'll go with 12 meters. Length of this room is 12 meters. So here's the question. How many Lawrences can I lay down, foot to head, and to cover the width of this room? How many Lawrences do I need to cover 12 meters? That's the question. Well, I can make conversion factors out of Lawrence in 66 inches. I can say 1 Lawrence, and we're going to abbreviate that LAW, is 66 inches. Or I could say 66 inches is 1 Lawrence. And the top and the bottom are equal to each other, right? If they're equal to each other, what is that ratio equal to? 1. Now, I learned in Miss Westheffer's 3rd grade that I can multiply anything times 1, doesn't change the number, right? So when you're multiplying by 1, you don't change anything. You change the units, right? But you don't really change what the outcome is. And I can make those conversion factors either one of 2 ways. Whichever way I need, I'll use. So the way we do this is we ask ourselves, what's the unit of the answer? So what's the answer? What's the unit for the answer? Number of Lawrences, right? So I want a Lawrence here. Right? In 12 meters, right? So what shall I start with over here? What I'm going to do is take something I'll start with that's given to me. I'm going to multiply it by 1 a bunch of times so my units cancel so I get the new units. And because I'm multiplying by 1, I haven't changed anything. Does that make sense? So what shall I start with? Someone say something. Yeah. Change inches into meters? You mean meters into inches? I could. That might be okay. Why are you going to use 1 Lawrence is 66 inches, which is the way I would have started it, by the way. I want Lawrence to be the answer on top, right? So let's start over here with Lawrence on top. 1 Lawrence is 66 inches. Lawrence is on the top where it needs to be in the answer. So now I'm confident that Lawrence is going to end up where it needs to be. Because I've analyzed the problem, I've analyzed what I know, I decided to start that way. Now I want to convert those inches into, you said meters, okay, but I don't know inches to meters. I know an inch to a centimeter. So I guess I'll do that first, right? So what goes on top here, inch or centimeters? Inch. 1 inch. How many? 2.54 centimeters. Okay, so inches cancel inches. And now it's Lawrence's per centimeters. So I want to get rid of centimeters, right? It has to be on the top. What needs to be on the bottom? Meters. How many centimeters in a meter? 100. Is there 100 cents in a dollar? Yeah. There's 100 centimeters in a meter. It's like there's 100 cents in a dollar. Okay, so centimeters cancel centimeters. And how many meters did I have here? 12. Do I have the answer in Lawrence's? Yeah, I do. Meters cancel meters, centimeters cancel centimeters, inch cancel inch. I got it in Lawrence's. Someone pull out your calculator and give me the answer. $7.2? Why did you give me the answer of 7.2 and not 7.267? Because I got two sig figs, right? 12 meters, 66 inches. I got two significant figures, so I give the answer in two significant figures. Does it make sense that I could have Lawrence lay down here 7 times and almost cover the whole thing? I think he'd fit. Pretty close anyway. Right? Pretty close. So we're close. All right. You okay with that idea? All right. So we took the height of Lawrence and made ourselves a conversion factor. These are some conversion factors that we've already learned, and we used those right over there, didn't we? Next question. How many seconds in a century? How many seconds in a century? So tell me some things you have to know to answer this question. How many seconds in a minute? How many minutes? Okay, how many seconds in a minute? 60. How many minutes in an hour? 60. What else you got to know? Hours in a day. How many? 24. How about days in a year? How about days in a year? Let's take a regular year. Yeah, 365 days in a year. We'll forget the leap year thing. And then how many years in a century? 100? Okay. Those are all things you need. And can you make, and they're all equal to each other, right? Well, not, I mean, each one has its equality, correct? So we could make those into conversion factors, couldn't we? All right. So what are the units of the answer? Seconds. And so over here, I'm going to write down seconds. And I'm going to start with 1 century, correct? Okay, so these are things you told me that we need. Was all of them? Yep. Okay. So we're going to start. We want to know how many seconds in a century. That's what we're asked to find. And I go from century to years. I go from years to days. My years here are going to cancel. I go from days to hours. My days are going to cancel. I go from hours to minutes. My hours cancel. I go minutes to seconds. And my minutes are going to cancel and give the answer in seconds. And there's the number. 3.1536 times 10 to the 9th seconds. I seem to have a lot of sig figs there, correct? Because every one of those has as many sig figs as you want them to be. They're exact numbers. So I can report a fair number of sig figs there. Now typically we would do no more than 3, but you can do a lot. Are we okay with that? Any questions on this? Lots of time, good. Okay. So these are conversion factors or things that equal to each other. These are the ones I've asked you to memorize. Learn those. Volume sometimes causes problems because 1 inch cubed is not 2.54 centimeters cubed. You have to cube the number as well as the inches, and it turns out 1 inch cubed is 16.39 centimeters cubed. So when you're doing volume and you're cubing something, you've got to cube the number and the unit. And I found a lot of freshman chem students have trouble with that. So I've just mentioned that here as a highlight because my experience is kids have trouble with this. And we're gonna do some of this here in a second. So density, everyone knows, is mass over volume. Typically for solids and liquids, it's gram per mil or gram per cubic centimeters. Densities are temperature dependent, but we'll typically give it at 25 degrees. Here's our recipe for dimensional analysis. This is the process that we've been using and that I expect you to learn to use. On the far right, put down the units of the answer, like we did over here, Lawrence. Analyze what's given and what you know to figure out what to start with. So we knew we had that conversion factor, we had 12 meters. We decided to start with Lawrence's per inch because Lawrence is on the top where it needs to be on the top. I analyzed my dimensions to see how to start. So I did that analysis. I used these conversion factors. I canceled my units. I did the numerical calculation. I wrote it down in the appropriate number of sig figs. So let's do this one. How many nanometers in 3.72 yards? Nanometers in 3.72 yards. What's the first step? Okay, who are you? Katie? Hi, Katie. How are you? Where are you from? Oh, okay, not far. Are you commuting or live on campus? Okay. Oh, Katie, you said do what?
Write down on the far right the desired unit.
And what do I want? What'd you say? Oh, I guess I got rid of it, didn't I? Nanometers. Okay. And we were given how many yards? Was it 3.72? Maybe we should look real quick. Yep, okay. Okay. What kind of units is that? Length, mass, volume, what is it? Length. What is this? Length. Oh, that's good. So I'm analyzing it so far and they're both length. But this is length in what unit? British, correct? And this is length in metric. Do I know a relationship that relates metric and British? Inches to centimeters. How many is that? 2.54 centimeters is 1 inch. So I've got to use that because I've got to go from a British unit to a metric unit. As I analyze these, it helps me begin to shape how to solve this problem. Inches and centimeters. Can you go from yards to inches? Can you do that? What's the relationship? 36? What goes on the top? What goes on the bottom? Yards on the top. Why yards on the bottom? So it'll cancel. So 1 yard is 36 inches. Yards are going to cancel yards. Okay? So now I got unit of length in inches. Now what should I use? Centimeters to inches? Okay, so inches goes where? Bottom. 1 inch, 2.54 centimeters. Centimeters to meters. Did that once. 100 centimeters is a meter. And 1 times 10 to the minus 9 meters is 1 nanometer. If you can do centimeters to nanometers, you can. If you can do it. What is it? Yeah, right, exactly. So you don't know. That's why you go to meters and then nanometers. All right. Okay, and anybody get that answer? Like, do the math? Anybody do the math? Oh, you're working on it? Okay. Well, 36 times 2.5 is about 100, divided by 100 is about 1 times 3, and that's 10 to the minus 9, so I'd say that'll go on top of 10 to the plus 9. 4 times 10 to the 9th would be a good number. We're real close. I think that's right. How many sig figs in the answer? 3. The 0 is significant. Everybody okay with it? Any questions? Kate, what was your name? Katie. Walk me through how we solved that problem. Just sort of so step by step. Just tell me in your loud voice how we solved that problem.
Okay. Well, we figured out what we wanted,
Which was?
nanometers. We knew what we had, which was yards. So then we found a connection between British and metric units, which was 2.54 centimeters equals 1 inch. But then we had to get yards to inches, and then which was 36. Then we had to get inches to centimeters, which was the 2.5. Then we had to get centimeters to meters to make it easier to convert to nanometers. And then we did the final conversion to meters to nanometers.
You can teach this class. That's right. Well done. Okay. Any questions for Katie? Are we okay? Is this boring? Is this easy? Be honest with me. Boring. How many say it's boring and easy? Three or four hands is all? Oh, okay. Then I guess we're okay. All right. Well, let's get a little more difficult. A major contributor to global environmental pollution is coal burning from power plants. Carbon dioxide, a greenhouse gas, is a major product, and all coal contains various amounts of sulfur that eventually contributes to sulfuric acid rain. In addition, the high temperatures in the combustion chamber in the coal burning power plant cause N2 and O2 to combine to form NO, the beginning of NOx. A typical coal burning power plant burns 2,500 tons of coal per day. The one in town does. That's their data. With a sulfur content of about 3%. The density of solid bituminous coal is 1346 kilograms per meter cubed. And for solid anthracite coal is a density of 1506 kilograms per meter cubed. What volume in cubic feet of bituminous coal is burned by a typical coal burning power plant each day? That's the question. So even you guys that are bored should be thinking, oh, this is cool. Does that look hard? Looks hard to me even.
It seems like there's a lot of information you don't actually need.
There might be information you don't actually need, because the next part of the problem you're going to need some of that information. But yeah, there could be lots of stuff you don't really need to solve the first part, but you might need for the second part. Seems to be a lot of stuff there. All right, so let's kind of sort this out. What's the first thing I do?
Find the units that you're going to use for your answer.
Okay, the units of the answer are going to be cubic feet per day, right? I want cubic feet in a day. What do you know about a day? They burn 2,500 tons of coal in a day, right? See that? 2,500 tons of coal a day. Let's write that down. That's got a day in it. 2,500 tons in one day. I got days where I want it. That's tons and that's feet cubed. What kind of a unit is this? Length, mass, volume, what is it? Mass, weight, yeah. What's this one? Length cubed, which is volume. So how do you relate mass to volume? Density. Are you given density? Yeah. What kind of coal are you burning? Bituminous. So it tells you the density of bituminous coal in kilograms per meter cubed. So I'm going to have to use that. I'm going to write this down. 1346 kilograms per meter cubed. Because I've decided I've got to use that someplace in this conversion. So if I analyze where I'm going and what I've got, someone give me some advice. Pardon? I'm going to use it. So I'm going to use that somewhere in this conversion factor. I can convert meters cubed into feet cubed. Okay. You think I should just stick this thing in here someplace? I could convert meters cubed to feet cubed. But where's the feet cubed have to be? On the top. So the length cubed has to be on the top, so I better say 1 meter cubed is 1346 kilograms. Because meter cubed to feet cubed. Let's do that. So how many, let's see, meters to feet? Oh, God. Do I know meters to feet? No. But what do I do? What do I know about meters? Centimeters. So 1 meter is 100 centimeters. And I have to cube that. Because meters cubed has to cancel meters cubed. That means I cubed the 100 as well. And then 1 inch is 2.54 centimeters. I've got to cube that, or I can write it down 3 times. So centimeters cubed cancel centimeters cubed. So I'm assuming if you're not writing this down, you've got photographic memory. Okay. Now what kind of units do I have here? Inches cubed. So I'm going to go from inches cubed to feet cubed. Can you do that? How many inches in a foot? 12. So 1 foot is 12 inches. I could write it down 3 times, or I could just cube it. So inches cubed would cancel inches cubed. And now I got feet cubed, which is where it needs to be. I got days, which is where it needs to be. But I got a problem. I got tons and kilograms, right? So I got to go from tons to kilograms. So I got to get rid of that somehow. That's a unit of weight or mass in what unit? British. That's in metric. What relationship do you know? Are you going to know? Grams to pounds. 454 grams is a pound, right? How many pounds in a ton? 2,000. Tons cancel tons. 1 pound, 454 grams. I could cheat and say 0.54 kilograms, but I won't. And 1,000 grams is a kilogram. So grams cancel grams, kilograms cancel kilograms. And lo and behold, I got feet cubed per day. I got the answer. Good job. There's the answer. That many cubic feet. About 100 million 2-liter Coke bottles. That much coal. All right, there's some more here. We're going to work them in next time. But this is the question. Is this dimensional analysis thing really important? Is it, it's pretty hard and it's kind of boring. Is it really important? Is it really important? So this was the Mars Climate Orbiter. That turned out was the Mars Climate Crasher. That cost you $125 million in the cost of the spacecraft, plus probably another $500 million in prep time, mission operation, and then trying to figure out what went wrong. That's your money. And what was the problem here? The root cause of the loss of the spacecraft was the failed translation of English units into metric units in a segment of the ground-based software. They couldn't do this right, and it became the Mars Climate Crasher. If you want to be a pharmacist and they say we want so many deciliters per milliliter, and what you've got is grams per milliliter, you better be able to figure out that conversion so you don't kill the patient, or so you don't crash the spacecraft. Okay. Any questions? Do I have all the information sheets from everybody? This is the first chapter. We finished the first chapter. Read the sections I told you to read. You got a lot of work between now and Wednesday. These notes will be online. And I'll really be dressed up this nice again. So when I'm wearing jeans next time or shorts, that's okay. Any questions? Did you get your money's worth today? Did you learn enough? Okay, that's the end. All right, see you all Wednesday. Go sign up for SmartWorks. Make sure you turned in the Kim information sheet.